Okay, we'll wait for another minute. Okay, did you guys see who the Nobel Prize went to? In physics? Yeah, so that's for it's partly related to or what they did for the transmon. Yes, that is the basis for transmon, but it's not really tunneling. What they call it tunneling. It's okay. Oh, yeah, energy quantization in electronic circuits. Superconducting. Okay, I'm going to end the poll. So let's get back to what we were doing yesterday. So I hope you're able to see the screen. So did you guys were you able to try different stuff with using Colab? I saw some people replied, but were you okay? I see one yes. Okay, so I hope you try these things out and try to go along with the exercises, because it's not really a spectator sport. So unless you put your hands on, we won't be able to make much progress. Okay, so let's see. There are some remarks. Bell is right in that his theorem proves EPR. Okay. Let's ignore Bell for now. We'll come back to those comments soon. Okay, so let's see. So yesterday we did the exercise 1, and today what I want to do is first create the Bell state, and you guys heard a lot from Dr. Gargi on the Bell's inequality, right? So we will actually run the test on our quantum computer and see what happens, right? Let's check that out. So if you don't have access to the code that I'm using, I'm going to paste it in the chat, but please make a copy of the file for yourself and do not run on this file. I repeat, I'm going to paste the link in the chat box. Please do not edit this file itself. Please make a copy for yourself, and then you can follow along. Is everyone able to see the things? And when you make a copy, please put your API token. Please put your CRN instance, because this will be using mine. So if all of you use the same thing, then it will get stuck. So click on the link that's in the chat and confirm that you have changed your API token and CRN instance to your own API and your own CRN. Is it opening for you guys?
Yes, sir.
Okay, so perfect. Please do make a copy, and I will wait for you to reply on API that you have replaced your API token and that you have replaced your instance, CRN instance with your own. So I'll give it 5 minutes so everybody is able to do that. Then what I want to do is I want to go back to exercise 2 and exercise 3 and then do the Bell's inequality. So once you have replaced run the first cell and the second cell by replacing API token in the instance, please reply done on the chat. Okay, we have one done. That's great, Tejaswini. Okay, great. Two done. Yeah, I always tell my students that one more year to wait for the next Nobel announcement. So we don't know, right? Maybe some names will pop up. Huh? Like, yeah, that's exactly the point. There is a finite probability, statistically, right? You cannot say it is zero. Okay, I see only two done still, three done. Okay. Okay, great, great. Okay, no problem. No problem, Saptagiri, take your time. Okay, great. Okay, Dell, thank you. Okay, we'll give it 2 more minutes until 5:10 so that everybody is caught up. And once you have done that, please run the cells so that you're ready, right? And then we already did exercise 1, so I'm directly going to go to exercise 2, unless there are any questions about exercise 1. Are there any questions on exercise 1? Okay, done. Okay. Okay, others, are you able to do that? Okay, great. 1 more minute until you have your own copy of the code so that you can follow along. And I hope all of you are able to create your own APIs and the CRNs. And if you're at any institution, you may also want to check with educational institution. Maybe they do have some access plans. I think IBM has given some access plans to some institutions. So maybe maybe you have some. I don't know. So maybe you want to check. I know some of you are at IITD, so maybe I think IITs have received some credits for some quantum computing, something like that. Maybe you want to check with your computer science department or whoever is leading there. Okay, so then let's go to the second part, right? So what we want to do is we want to create a 2-qubit state, right? And then we remember that the qubit ordering is reversed. That is, if I have, if I write, remove this. If I write, usually when I write something like this, 0, 1, this, when we write, we think of this as qubit 0 and this as qubit 1. But in case of qiskit, when we create a 2-qubit computer, right, Q0 is this is Q0. On qiskit, Q0 is the rightmost one. So the ordering is different. So remember that, right? So you always have to go from the rightmost end, right? So rightmost bit is the qubit 0. Okay. So we are creating a, I hope everybody is now able to understand what this means. We are creating a quantum circuit with 2 qubits and 2 classical bits, because we want to be measuring, right? And we're applying H is the Hadamard gate. So when we do this, I went through the entire lecture of transmon, what transmon is, and how do we apply this. So when somebody asks you, how do you do a Hadamard gate, please do not answer, oh, okay, it is just this. This doesn't tell me anything about how you're applying Hadamard gate. This is just mathematical form, right? So how do you apply Hadamard gate? You use microwave resonators and you apply different pulses with different times, like we discussed. I hope you recall. If you can't recall, please go back to that PowerPoint and see, because you need to get back to experimental hands-on and see how it is actually done. Otherwise, it's a bunch of code that you're running and it is meaningless, right? So please bear in mind that the Hadamard gate is, you're getting that by applying a perturbation to the transmon qubit through microwaves. And so you apply the microwave for a certain time, and that's how you flip, get this matrix, right? So we apply the Hadamard on the first one, and then C naught on the second one, right? And that's how we're getting the Bell circuit, right? We are creating the Bell state that was in the homework. So we're creating this state. Are you with me? So when we start with 0, 0, right? Then I apply Hadamard gate, right? I get then I apply Hadamard gate only on the 0th qubit, so I'm getting 0, 1. Remember, this is the 0th qubit on qiskit, and then we get 0. Sorry, we get 0 with 1 over square root 2. We're applying on qubit 1, so we get 0 plus 1. Right, rightmost qubit is the first qubit, right? So when I do this. When I do this, I created this state. I created this state 0, 0. And this is qubit 0, and this is qubit 1 on qiskit. So then when I apply Hadamard gate, that is, I apply a bunch of microwave pulses, then this 0th qubit is becoming a superposition. Are you with me? Are you able to see that? And then we're applying a NOT gate, right? A C NOT gate, right? So then you would get 1 over square root 2, right? You get 0, 0, right? Plus 0, 1, right? So when you apply a C NOT gate for 0, 0 will give you same thing, 0, 0, it doesn't change. Only if you have this, this changes to 1, 1. So then that's how you get the Bell state that we wanted. Is that clear? Are you able to follow that?
Yes.
Okay, great. So then we created this 5 plus state, right? Okay. Okay, so now let's get to measurements. Let's see whether we see what we expect. So now you have heard EPR and elements of reality and stuff. So we have this state 5 plus. It's equal to 1 over square root 2, 0, 0 plus 1, 1, right? So now if I make measurements if I measure both Q0 and Q1, what is the thing we expect? We expect it to show up as, correlated. This would be positive correlation, like both. If I find Q0 to be 0, Q1 must also be 0. If I find Q0 to be 1, Q1 must also be 1. Do you agree? Yes? Okay. So here, that's what we're doing. So we are setting Hadamard gate. So we got to, so this is the Hadamard gate. So we got to first Then, sorry, this is the Hadamard gate. Then we got here, and then we applied C0 gate, and we got here. And after that, I'm measuring Q0. That M is measurement that you see here. And the other M is measuring the qubit 1. So qubit 0 and qubit 1. I'm measuring the qubits and storing them in the first classical register and the second classical register. So after you have made the circuit, remember you have to transpile it, meaning that you have to tell the computer, what that means so that it can apply the right pulses. So we are going to run that, and we are going to run that for 2048 shots and see what we got. We got 11851 times, 00934 times, but I'm also getting 0, 1 and 1, 0. You see? So it's not always that if qubit 0 is 1, qubit 1 is always 1. There are instances where qubit 0 is 1, but the other qubit is 0. Where here I have qubit 0 is 0 and qubit 1 is 1. Do you see that? So you can plot the conditional probabilities. By conditional probabilities, I mean, I want to see when Q0 is 0, what is the probability that Q1 is 1? And what is the probability that Q1 is 0? So let's see, right? If you plot that, you can see conditional on Q0 equal to 0. We created this state. So what we would expect is that we should get with certainty that Q1 must be 0. But are we getting with certainty? Are you guys following me? No. Very good. So what that means is that you are not getting it with certainty. That is, in realistic systems, in real quantum ensembles, you always have, at least on the quantum computer that we are using, we always have the other outcome that I cannot predict with certainty, that if Q0 is 0, that Q1 is going to be 1, right? So I got now, Q1 is equal to 0 and Q1 is equal to 1. So let's see, maybe let's change the number of runs, right? Let's change the number of runs. So here I did 2048 shots, right? So let's say we do only 1024. Let's see what happens. So I'm still getting, non-zero ones here, right? Are you able to see that? So you can do that for, as you increase the number of shots. I don't want to, okay, let's go ahead and increase. If the time gets over, then we'll see. Let's say we do 5,000 shots. So if it is like coin toss, then this is due to gate errors. So the error percent is not this much, right? The error percent is only 8. So there is preparation error. I don't want to say preparation error. We'll come to that. How about I come to that? Just give me a second. I'll come to that, Shafna. It is not due to noise and decoherence either. Because we are making our measurements. Recall, that's why I went through the transmon things very, very carefully. It takes around few nanoseconds to make a measurement. The coherence time is around 100 microseconds, almost reaching a millisecond. So when we are making measurement in a few nanoseconds, there is no decoherence. And actually, we can delay the measurement and show that it is actually not decoherence. But that's going to be an exercise, and I'm not going to do that explicitly here, but you can delay the measurement. So what you could do is you could add here a delay switch. After Hadamard and X, you add a delay switch. That is, you delay for some X seconds and then measure it. If it is decoherence, then you should see that 1 has become 0. But you would see that that's not the case. So it is not due to decoherence. There is gate error or preparation error, but I don't want to call it error. So when we like, the reason is that when we're preparing the state, the only way we know what state we have prepared is by measuring. So I do not know until this measurement happens what is happening, right? So the measurement compounds whatever has happened before it. And when we are saying you are preparing a state, we are not preparing a single particle. We're preparing an ensemble, right? State preparation means, an ensemble that fixes the probability distributions. So this is my probability distribution for this Hadamard and X gate. It is just that we sort of think about this like this, but that's the state that it is generating, right? That you cannot generate 0, 0 or 1, 1. You always have some spillover with 1, 0, 1, 0. That's what it means, that you have to consider it as an ensemble. So we ran it for 5,000 times. So let's see what happens if the probabilities have changed. No, it's still a big chunk. So for example, like 250 times, you're getting out of 2,000, that's roughly 12%, right? So that is more than what we found is like failure of state to be prepared in the right 0, 0 or 1, 1. So you cannot attribute this to gate error or decoherence or noise. This is how quantum mechanics is, that if you think about single particle, that's when the problem comes. Like, for example, now we do the same thing with simulator, right? Here we're building the Bell state. Everything is exactly the same, except I'm not running it on the computer, but I'm running it on the simulator. And then you do see that, it's fully conditional, right? Are you able to see that? That you don't see anything here. You only get 0, 0 or 1, 1. Are you with me? Were you able to run it? So the question remains, right, that what is state? What describes a state, right? What describes a state? So we cannot really call each particle as having a state. We are, again, talking about an ensemble. So in a realistic system, you always get 0, 1 and 1 zeros, right? And that's what we see here. Okay, now then let us try to do the CHSH inequality, right? That if we check the fidelity between the idealized and the initialized state, then we will be able to distinguish. No, Shafna, you will not be able to distinguish, because ultimately you have to measure. So whatever errors you get have to be measured. So for example, let's say whatever state preparation I have, I prepare the state, right? Whether you have gates or whatever it is, ultimately you have to measure. So this measurement compounds all the errors before it, right? And yesterday we have sort of talked about this, that we initialized the state and we saw that the error should increase, the gate error should increase if it is the preparation error, but it did not. So there is measurement error, but there is very little error in the way the gates work, right? And recall that this is not at room temperature, this is at millikelvin. And so I would think that this is not due to gate error or preparation error. Whatever errors you see, some error will be due to the measurement, but that is roughly 5 to 8% is what we are seeing. But the kind of 0, 1, 1, 0 states we see are 12 to 15%. And that is for 0, 1. And again, for 1, 0, also 12 to 15%. So if you look at the total, that is 24 to 30%. This cannot just simply be explained by measurement errors alone. Okay. Any other questions? So let me pull up the EPR document. So I guess you should be able to see that now, right? So what Dr. Garge derived is this part, right? So here what we had And that's what we are going to simulate with the real quantum computer now, right? So when we say C of A B, right, that means I am doing the correlation, right? For that, what I need to do is I need to have A of A, whatever, lambda, and B of B lambda, right? So I have to have some measurement device that is measuring along a-axis, right? So let's say x-axis, y-axis, right, and some axis in between. So I'm going to take two axes that are separated by pi by 2, and then I'm going to take one axis that is a prime. So let's say a is x-axis, b is y-axis, a prime is 45 degrees to x, and b prime is negative 45 to x, right? So then I could draw this as my a, which is x-axis. This is my b, which is y-axis. And this is my a prime. And this is my b prime, right? Oh, I covered it up, I guess, here. Can you see that now?
Yes.
Yeah. So we are trying to test the Bell's inequality. And so we have prepared a Bell state, right? And the Bell's inequality is given by this part. So for doing this, we need 4 different directions to make the measurements. So I'm just picking A to be X, B to be Y, because A and B are orthogonal, right? So I'm picking them to be at 90 degrees to each other. And then A prime, B prime are also orthogonal. So it's like you're rotating by 45 degrees, right? So A prime is 45 degrees to X, and B prime is 45 degrees to Y. All right. So then we can make these measurements on the Bell state and compute this thing and see whether we get that to be less than or equal to 2. Right. So if Bell's inequality is less than or equal to 2, then it is not violated, right? Are you with me?
Yes.
Is everybody able to follow? So what do you think? Bell's inequality should be violated or should not be violated? Should be violated, should be violated. Okay. So maybe let's make this a should Bell's inequality be violated. I want to make it a poll. So should I put a choice of 1 over square root 2 yes plus no? That would be useful, I guess, right? Okay. Okay. Are you able to see the poll? Are you? So if you say that it is violated, that means whatever we compute should come out to be greater than 2, right? But is it going to come out to be greater than 2? We'll see. Yes, one of them replied no. That's good. I don't think Bell's inequality is going to be violated when you run it on a real quantum computer. That's what I'm guessing. But let's see. Have all of you answered? Some of you are undecided. Okay. So 77%, participants participated. So 4 of you still haven't voted. Please do vote. Okay. Okay, let's see. So are you able to see the results? So a lot of you think that, yeah.
Yes.
So a lot of you think that Bell's inequality should be violated. So we are going to, that is, by Bell's inequality, we mean this inequality that is on the slide up here, right? So we're going to calculate this and let's see if it is violated or not. I think it's going to be barely going to be violated. Let's check, right? So so in fact, that inequality, this is called actually CHSH inequality. It is a re-derivation of Bell's inequality in a different way, but it tells the same kind of has the same content, right? So let's see. So we are building the Bell circuit again the same way, right? I hope you were able to um, follow along when we did this a couple of minutes ago, right? Hadamard gate is going to put, so we're creating qubit with 0, 0. This is always the initialized state. So Hadamard gate is going to act on the first qubit, which is the rightmost one. So this is going to give us after QC dot H0, right? We get the first, this is going to be remaining same, but this is going to be in a superposition. So we get 1 over square root 2, 0 plus 1, right? And then we put, so that is equivalent to writing 0, 0, right? Plus 0, 1, 1 over square root 2. And then we are applying QC dot CX. This is the C naught gate, right? C naught gate. So the C naught gate makes this into 1, 1. So we get 1 over square root 2, 0, 0, plus 1, 1, right? Right? So that is the 5 plus state. So then we are going to, rotate, like I said, A and B, right? We have 2 directions. So we're going to pick A to be 0, that is the x-axis, right? Then we are going to pick pi by 2, that is going to be y-axis. And then A prime, B prime are going to be 45 degrees offset. So, okay, there's a question. So these are, we are defining how we are going to measure. And we are going to measure both 0 and first qubit and store them in 0 and 1, right? And so, and we are making these settings. Instead of C, I'm calling it E. Usually it doesn't matter. So we are going to measure E of AB, E of AB prime, E of A prime B, E of A prime B prime, right? So that's what we need, right? E of AB, AB prime. So each of these 4 components we are going to measure, right? So we're setting that up. And we're building the circuit. So when I say Bell builder, it is building the Bell state, right? And then we're going to just basically have the rotation axis, right? Whatever we set up. And then we're transpiling this to pass it on to the computer. And we put the backend as IBM Torino or whatever is the least busy. And then we're going to get these correlations of probabilities of 0, 0, 0, 1, 1, 1, so on and so forth. And then we're going to make the measurements and get the counts. So let's see. So now the Bell's inequality came out to be 2.827. So it is violated in this case, right? Are you able to see that?
Yes.
It came out to be greater than 2. Let's run it again and check. Sometimes you will get it to be not violated. Okay. So let's change the number of shots to 2048. It's still violated. Sorry? One shot. Okay. So we want to do one shot. Let's see what happens if we do one shot. If I do one shot, will it be violated? I'm getting one shot to be 4. There is something wrong with this. Yeah. So one shot, 2, 2, 0. There you go. It's not violated. So it depends, right? So as you accumulate, you keep getting different results. So it is not, again, single shot measurements. So okay, Anuradha shared that. Okay, thank you, Anuradha. For single shot, yeah, it varies. Yes, that's the point I'm trying to make, Saptagiri, that when you talk about Bell's inequality, often people talk about single particle measurements, and what we're trying to say is that is not completely correct. That we talk about correlations, overall correlations, not about just single correlation. So right now here, what we have made is not actually a singlet state, because here I have 1, 1 and 0, 0. So what we want to make is a singlet state, right? So we made the singlet state up here. So now let's make the singlet state. So singlet state is this. Let's go here and make the singlet state. So I'm making singlet state now. So this is how you make the singlet state. So we got this. This gives you the state 5 plus. That is, I have both to be 0, 0 and 0, 1, 1. Right? Then I apply the NOT gate. X is just NOT gate, not C NOT, just normal NOT gate on only the first qubit. Remember, the first qubit is this one. This is the first qubit, right? Then I apply only on the first qubit, right? So then I get basically 1, 0 plus 0, 1, right? Are you able to see that? That when I apply this, I get the singlet state. Yes, Rajneesh, violation is dependent on the number of shots, meaning that if you do just one single shot, that doesn't tell you anything. That is, we cannot say, like, the state itself is not a property of the particle. That is what we've been talking about, that when we talk about state, the state itself means ensemble, that there is no state attached to one single particle. So if you try to talk about it as a single particle, it leads to unnatural interpretations that are not necessary. But if you consider it as an ensemble, then you don't have to worry about that. I hope that answers your question. Yes, CHSH is sort of like Bell's inequality, but more. So Bell wrote it from a theoretical point of view, and CHSH is more written by for like experimental measurements. I would say, like, experimentally, CHSH is what we can, like, the form in which you write it, express it. The inequality, the essence of the inequalities is the same. It is just the form in which you write. In case of CHSH inequality, makes it easier to verify in terms of experiments. I hope that answers your question, Saptagiri. Okay. So now we built a singlet state. So let's see. Let's do the measurement now and check. Okay, I ran it only on one shot. So let's make it 1498. So let's see what happens. Okay, so modulus of S is greater than 2, right? We got 2.81 for singlet state. So so are you able to see that on your own screens when you build the state? Are you with me? How did they come up with this upper bound too? So that was what the last lecture was about, right? So because when you measure the spin, right, the anti-correlation, then you should get, either 1 or -1. And so when you do the math, you will get the modulus values. It would be like 1 plus something, and that plus something can only be at max 1, because the result has to be between -1 and +1. So that's what gives you the upper bound of 2. So if Bell's inequality is violated, that means quantum mechanics is not a complete theory. That's what I think, that it's statistical. So you can run more with with these codes. You should be able to go back and do different states and try to. You are actually doing the actual experiment, actual Bell's inequality experiment, which is pretty cool. And you could also see, like, you could also try to change this to something else, some other theta. Instead of pi by 4 minus pi by 4, you could do some other angle. Let's say I do if I do pi by 3, right? So let's see what we got. You still get, it to be violating the bound, right? So you can check out for different angles, different states, and see what is happening, right? But when we make the Bell state itself, as I have shown you before, up here in the simulator, you get this, right? But in here, in real quantum computer, we get, non-zero probability of it being 0, right? So that's called one of the loopholes in proving this experimentally, that you cannot really prepare this state, right? Are you able to follow that? Any questions on Bell's inequality so far and how we did it experimentally? Okay. Why you thought it wouldn't violate? I was just kidding. Because there was one reply when I put the poll that somebody said no. One reply was no. So I was just kidding. Yes, that's right. I was trying to confuse as well. So to see what you would think, right? But I mean, that's the point, is that no matter Einstein or Heisenberg or whoever, whatever they think, it doesn't matter. Ultimately, experiment, tells you what it is. So it is violated, and so that means that Bell's inequality is violated. Then that means that quantum mechanics, the way that was derived, to me, it looks like that it is. I would just say that it is not complete theory, meaning that you can only predict statistics. That quantum mechanics is inherently a statistical theory, because recall what was the definition of in EPRA that Dr. Gargi showed, I guess I can go back to the thing here. EPRA, is that EPRA argument? Yeah. If without in any way disturbing whatever, we can predict with certainty. What does certainty mean? Certainty means zero entropy, right? Or there is no statistics. If I can say it is definitely heads, there is no statistics, there's no probability. So if there is no certainty, then that means that this criteria of reality is not satisfied. That meaning that I have a statistical theory. I don't have something that I can predict with certainty. I can only predict probabilities. Are you following me? Yes. Okay. So that is what Einstein was trying to say, that if you accept that, not in this paper, but I think it was in another paper that he was trying to say that if you accept that quantum mechanics is inherently statistical, then that means that there is no need to invoke things like, okay, there is faster than light communication that is going from particle 1 to particle 2, somehow telling it that it should flip or something, right? So this violation is indeed true. We have verified it, that it is violated. That means that there must be something that is violated in the argument, right? We have EPRA, EPRB, which was locality, right? And then EPRC was the completeness of quantum mechanics, right? So all that this shows is that quantum mechanics cannot predict single outcomes with certainty. It is a statistical theory. So basically, we do not know what exactly is happening. Hence, we are talking about probability. Yes, we cannot say it with certainty. That's right. We cannot say with certainty. And also, my personal understanding, I could be wrong, is that when we have, like, suppose, like the singlet state, like 0, 1, 1, 0, right? This is an entangled state, meaning when we talk about this, we cannot, making a measurement on one of these is disturbing the system, in my opinion, because you cannot talk about this as two systems, but one, the entire thing. Dr. Gargi is shaking her head, but I feel that uh, that we cannot make a measurement without disturbing the system. That's what I'm trying to say. That I don't know if EPRA is satisfied, but ultimately this no matter what interpretation it is, the take-home message here is no matter what the interpretation is, this is violated. I hope you're able to see that. And that's actually leads to the part of the confusion that we do not have specific outcomes that can be predicted by specific interpretations that could help us verify, which interpretation is right. And that's what Einstein's problem was also. But overall, what it does show is that quantum mechanics cannot predict outcomes with certainty, that it is only statistical theory. And the other thing is that this locality also includes separability, that assumption that we can separate these probabilities. But in reality, maybe we may not be able to separate these probabilities. In other words, this inequality is violated no matter what, but the explanation for that violation could come from multiple points. That's what I'm trying to say, that it could be that quantum mechanics is incomplete, or it could be that quantum mechanics is non-local, or it could be that the hidden variables or whatever is not separable, meaning that I cannot separate these out. So the Nobel Prize was given for saying that it was non-local, but it could be non-separable. It could be that quantum mechanics is an incomplete theory, and just is statistical. Any discussion on that? Any questions? Are you guys don't have any questions, or you're confused? Anyone? Any questions here? Okay. We lost precious 30 years between EPR and Bell, right? We did lose those precious years between EPR and Bell. But actually, in between EPR and Bell, there was David Bohm who wrote. So EPR first, then David Bohm, and then Bell. So there was a lot going on with David Bohm there. Any other questions on EPR or Bell's inequality? Bell get Nobel for this? Huh? Well, we can ask Bell Nobel, right? So that I don't know if he got a Nobel for this, but I think he got some other awards for it. But did he get? I don't think he got Nobel for this. Any other questions? Oh, he passed away. So Einstein's issue was with the interpretation, not the theory itself. I mean, interpretation is a part of theory, right? So what Einstein was trying to say is that when you talk about state preparation, that state is not for a single particle. That is the ensemble. That is, you have to consider that quantum mechanics is inherently statistical. Yes, Clauser-Alain aspect and Zellinger were awarded recently. That was with photons. That's what was done. But Bell himself passed away, so it's not awarded posthumously. So I hope, Veer Roy, I hope I answered your question. Do you think it would be possible to predict and recreate the exact behavior of a single quantum particle? Again, that is the point, that when you say a quantum particle, single quantum particle, we cannot associate the state with a single quantum particle. So when we talk about a state, when we talk about a quantum state, we are automatically talking about an ensemble. We're automatically bringing in statistics. So there is not real much meaning to talking about single particle measurements. It's inherently statistical, means no certainty. That's right, Mahesh. Shafna, does that answer your question? Isn't that also no cloning? Again, no cloning is also for the state. That is, you cannot clone the state preparation itself. Because if I can clone the state preparation, then I can measure different variables on different experiments and come back to certainty, right? And so the no cloning is for the state itself. You cannot clone the state itself, not the particle, right? Again, the state is state preparation, like the ensemble. So whenever we're talking about no cloning, it is for psi, the state, not for the particle. Anything else? Instead of QM, we need some other formulation to talk about. Again, there is no single quantum particle. That is the thing. It is inherently statistical. That there is something at a particular level that we cannot predict with certainty. That's it. That you have to accept that as what it is. So because we cannot prepare with certainty. That's what we're saying. So when we talk about quantum, that's the definition of quantum, meaning that I can only talk about a probability distribution. So that so there is no single quantum particle. When no certainty, what could be its limitations or merits? it still allows us to predict expectation values, which would be very useful in experiments, right? We can, whatever we're doing, our expectation values, we can still predict the statistical distributions. So that still gives us a lot of information, right? So like, for example, your computer, not even quantum computer, whatever your computer, laptop, phone, everything is possible because we can predict expectation values. Um, uh, Quantum weirdness comes in because you are considered, if you consider state as property of a single particle, that's where the quantum weirdness comes in, and you get all these unnatural things like all sorts of explanations, which are like electron is interfering with itself, and like the superluminous uh, faster than light communication and spooky action and all those kinds of things. But if you accept the fact that quantum mechanics is inherently statistical, then it's not weird anymore. That it is just statistical. Yeah. So this again is our limitation, right? Meaning it is a natural limitation. It is what it is. That's how nature is. Yeah. Well, that state preparation is uh, statistical, that there is no certainty, that you can only get a probability distribution. Hard time accepting that. That's okay. A lot of people do not have easy time accepting that, right? So that's why we call it the shut up and calculate, because every time, like any discussion between physicists that involves Bell's inequality or Einstein's APR paper ends up with, okay, let's just shut up and calculate stuff, because ultimately if you just shut up and calculate, the whatever calculation, this is going to be less than or equal to 2. The math is what the math is. So people just go back to shut up and calculate. Um, so so you're not alone in that sense, Shafna. Any other questions? Okay, so tomorrow we are going to start with quantum information, and this was a prelude to quantum information, because we're going to be talking about the sort of how we're going to exchange information between two parties, and then we're going to talk about quantum channels, and then run these quantum channels and different um, dephasing channel, depolarizing channel, so on and so forth, on the real quantum computers again, and check theory versus prediction, and look at what is happening. So if you have any other questions, I'll hang around, but if you do not have any other questions, this would be it for today, and then we can meet tomorrow at 3. Yes, as Dr. Gagi pointed out, please play with the code, make a copy for yourself, and see if you find anything interesting. Okay, so if there are, could you please suggest some references that covers yesterday's and today's lectures? Um, Yesterday's and today's lectures, it should be, so for example, for today's lecture, there should be references up here, right? So you can see the references that Dr. Gagi is going to send out, uh, Dr. Gagi is going to send out, so you can see the references here, right? And even yesterday's, the book should be mentioned in the PowerPoint. So maybe I would go to those references, Subhanshu. Any other questions? Okay, in that case, we'll see you tomorrow. Thank you.